Alright, well welcome to CSE355, Computer Networking for Engineers, lecture number 9. Here's our pregame question for today. Assume that 3 people check into a hotel. They pay $30 to the manager for the room. The manager then realizes that the room rate is only $25, so he gives $5 to the bellboy to return to the guests. The bellboy decides to pocket $2 and returns $1 to each person. So each person now has paid $10 and received 1 back, meaning that they each paid 9, which totals $27. The bellboy has another $2, which only totals 29. What happened to the other dollar? I'll give you about a minute to think about that. Okay, and the problem that we have here is just in the simple math. So the bellboy decides to pocket $2 and returns $1 to each person. Well, that's the $2 in his pocket plus the $3 that he's now returned to the people. Each person has only paid $9, which totals 27, and the other $3 would be the $3 that the bellboy has given back to them, not the $2 that he still has in his pocket. Alright, so let's move on to our lecture for today. We're going to continue with our discussion of Chapter 4.7 from Andrew Tannenbaum's Computer Networks. So to start, just a review of the different networking hardware that we have. We have repeaters or amplifiers that operate at layer 1. The main purpose of a repeater is to make sure that the signal is repeated as it goes across the wire or across a wireless network. Signals degenerate over time. This could be due to a number of reasons. Attenuation is one that we have already discussed, as well as outside noise coming into the wire. So repeaters are going to continue propagating a signal once the signal starts to denigrate a little bit. An amplifier works in a similar way where it's just going to take the signal coming in, amplify it, and send it back out. These are both layer 1 devices. At layer 1 as well, we also have a hub. A hub just has a wire, and all of the cables that are coming into the hub connect to the wire, and we end up with a shared bus. We talked about different strategies for having multiple channel access on a hub in one of our previous lectures. A switch operates at layer 2. This is where we're starting to add a little bit more intelligence to our devices. The switch is able to open up the frame, read the header of the frame and the trailer of it, and it will grab the MAC address from the header, and it's now going to forward that frame only to the output line where that MAC address will be. So let's say that we have 5 different lines coming into a switch, and the first computer is sending a message to the 5th computer. When the message comes in on the first line, The switch is going to read and find that the destination hardware address is computer 5, and it's going to forward that frame only to port 5, and it's not going to forward it along to ports 2, 3, or 4. A hub would have forwarded it along all of the different lines. Since it's a shared bus, there was no real forwarding involved, that the same frame would have appeared along all of the different output lines. A hub also has the repeater and amplifier built into it because there is outside power coming into it. Moving up to our next component, a bridge also operates at layer 2. The purpose of a bridge is so that we will have, if we have two networks that both are communicating with different hardware protocols, a bridge is going to allow them to communicate with each other. The bridge has at least two interfaces on it, one of them for each of the networks. So potentially we have an Ethernet network on one side, and then maybe we have a different type of a network on the other. And the bridge is going to allow us to communicate through both. One application of a bridge historically was to allow a wired network to communicate with a wireless network. We've gotten around that now by moving up to our next component, which is a router. And we have wireless routers that also have wired ports built into them, which is a switch built in. And so that takes care of the wired components able to communicate with the wireless components, because the router implements a switch inside, and the router takes care of the wireless communication for us. So the router operates at layer 3. This is the network layer of the OSI model. The router has some specific purposes, with one of the primary purposes being routing. And this is how our packets are able to make it from a source to a destination. Moving up to layer 4, we have a gateway. And gateways typically sit on the edge of networks. They operate at layer 4, so they're able to see the transport protocol, whether it's TCP or UDP. They can look inside of the segment at layer 4 to determine some more information about the data which is transmitted back and forth. Each of these components has a device associated with it. I have a few of them that I would like to show you here. Okay, so first of all, let me show you a hub. So this is a hub. On the front there, if you can read that, it just says that it's a hub. It is a 10 base T Ethernet hub, which means that it's going to be operating at 10 megabits per second. A 10 base T means that we have Ethernet cables that can be connected into it. It says that it's a 4-port hub. When I switch this around to the back, you can see that there are 5 ports on it. We have this port here is our uplink, and then we have 4 other ports to connect to. So what you would probably have is, let's see, this port here would be connected to your router, and then these other 4 ports would allow you to have 4 devices connected to this hub that would all be able to share the same line and have access to the network. The next component I have here is a switch, and this is a really nice switch that I have. It's a small one also. You see that it looks very similar to our hub. There isn't much difference to it. You have to know exactly what you're looking for from the front. You're not going to tell the difference unless you happen to be able to read it, where it says that the top one is a 10, 100, 1000 switch. So this is a 10, 100, 1000 switch, which is a gigabit switch. It also has 4 ports. When I flip this around, you're going to see a similar arrangement where we have our one uplink, and then we have the 4 ports that allow us to have 4 different devices connected to this switch. Even though the outside doesn't look much different, the inside absolutely has some differences, and there's a lot more intelligence in the switch than we have in the hub. Also notice, let's see, we have the power connector here on the back, and on the hub we have the power connector on the side. So this is going to allow us to have these devices also act as amplifiers for any of the data that comes in. I don't have a bridge on hand, but I do have our next component, which is a router. I have two different routers, so I'm going to show you the first one here. This is a Linksys router. It's a little bit older router. It's only an 802.11b, so we've gone through a few iterations since then, which is 802.11g and 802.11n. This is a 2.4 gigahertz. We do have the dual band routers now as well that are not just 2.4 gigahertz, but they also operate at the 5 gigahertz level as well, which allows us to communicate at two different frequency levels. If I flip this around, this was a wireless router also, so you see it's got the little antennas. We don't have these so much on the newer routers, but the older ones had them still. If I flip this around, you will notice that this is also an Ethernet switch. So we have our things to plug in back here. If you want to use this solely as a switch, then you have these four for plugging components into, devices into, and this is our uplink, just like we had on the switch and on the hub. On the other hand, this will operate if you have a wide area network connected directly to it. Then we have our WAN connection that can go in here. This isn't necessarily as important nowadays since we have modems that come in and we have the Ethernet cable that's going to come off of the modem directly, and so that then is going to be plugged into one of these other. We probably wouldn't use this wide area network with the way that we typically have things arranged nowadays. Here is another router. This is a Belkin router. You see that it's much more stylish. It's a newer one, and there's not really much to the outside of it. The antennas are built into it. If I flip it around here and show you, we have the Ethernet ports on the back there, so this is also a switch. We have the 4 ports for the switch, and then this one actually allows us to connect the modem into it as well right here. So what we have is we will have 4 other components, plus we're going to have our component going out here, our cable going out to a modem on the top port. The USB cable connection down here would be for configuring. If you didn't have a network connection, you could configure this router through a USB component, and then down here we have the power as well. Okay, so continuing on now, we are going to talk about the network layer a little bit today and IP addressing. So routers operate at the network layer, which is layer 3. Most routers nowadays are going to operate over IP, which is the Internet Protocol. There are other layer 3 protocols, but the primary means that's used on the Internet is over IP. Most modern routers today contain the following components. They contain routing software, which is the primary purpose of a router, making sure that our packet is able to travel through the network and get from the source through the network to the desired destination. As we've talked about, the way that packets are routed, there are a number of different strategies, but to have a relationship to the physical world, think of the postal service. You send a letter and you write the address on the front of it. We don't know how it gets to the destination. We take it to the post office or we drop it in the mailbox. The mailman picks it up and then they start it on their routing. Now, when they route it, they don't necessarily say when we drop it off in Dallas that then it's going to be routed through Houston, then it's going to be routed through Salt Lake City before it ultimately makes it to San Francisco. But instead, Dallas says, well, maybe it's going to be better if we get it to Houston, it's going to be closer to where it needs to go. So they route it to Houston, and then the mail carriers in Houston look at it and say, well, if now I take this and route it to Salt Lake City, that's closer to where it needs to go. And then they send it to Salt Lake City, who does the same process. Ultimately, it's going to make it to San Francisco. It doesn't mean that this is the most efficient way for it to get there, and there are a lot of metrics involved in this for whether this is the shortest way, the fastest way, the most dependable way, or a number of other quality of service metrics that we will discuss. Most routers also contain switches. You saw the two that I showed you just a second ago. Both had 4-port switches on the back of them. Most routers also will come configured with firewalls. A firewall is just a component that is going to block all incoming ports. Ports are going to be set in layer 4. However, a firewall is going to allow us to block any ports that we don't want coming in. Such as if we only want traffic to come in over HTTP, which would be port 80, we can configure that all other data will be blocked and only data coming across the line on port 80 will be allowed through. NAT is an acronym for Network Address Translation. This is how we can have local IP addresses or private IP addresses within a network, even though we're going to have the ability to be accessed from outside of the network using a public IP address. The router would typically contain the public IP address, and then the computers that are inside of the network would be NATed, Network Address Translation, so that they would have private IP addresses. When somebody wants to communicate with one of the computers on the inside of the network, they would specify the public IP address of the router. Once the router receives the message, it would be intelligent enough to figure out the computer to which the packet was destined. We'll talk about NATing a little bit more when we get to public and private IP addresses today. The DHCP server, this is the Dynamic Host Control Protocol. DHCP is a mechanism where individual computers that would like to join a network do not have to have IP addresses and subnet masks and gateways all configured statically on them, but they can request for a DHCP server to provide them with an IP address and the subnet mask, the gateways, the DNS servers, and so on. So all of the information that a computer needs to be able to communicate on the network can be retrieved from a DHCP server. All of these functions are typically built into most modern routers nowadays. So we talked about IP. Here is the IP version 4 header. The IP version 4 header consists of a number of different fields. You see there that it's 32 bits wide. So the version is going to take up 4 bits, which is the version of IP that's being used. In this case, since it's version 4 of IP, it would always be 0100. The idea behind this field was that hopefully it would expand at some point and be extensible to other versions of IP. However, when we bumped up to using IP version 6, we ended up with a new header. So the version field kind of got stuck always having 0100 in there, which is the binary for 4. IHL is the Internet Header Length. Tells how long the header is in 32-bit words. So it's going to be whatever the number is that's in the IHL is going to be multiplied by 4 bytes. 4 bytes is 32 bits. And that will then tell you the length of the header. The minimum value is 5. And the maximum is 15, so the maximum header size that we have is 60 bytes, which is 15 times 4 bytes, which is a 32 bits, and that would give us 60 bytes. This is the maximum size of an IP version 4 header. The reason that we have this field is you see at the bottom of the IP header, we have the options, which are 0 or more words. So down here we have the ability to have a dynamic header that's of different length. The type of service field was intended to distinguish between different classes of service, such as reliability and speed, though most routers ignore this field. So the creators, the inventors of the IP version 4 header thought that maybe we can have different classes of service distinguished by this type of service header field. But it didn't end up working out that way, since most routers didn't implement reading that field. Total length is 16 bits, and you see that the maximum length is 65,535 bytes. This would be 2 to the 16, so the value in the total length represents the number of bytes that we have inside of our entire packet. And so we have 16 bits, 2 to the 16 is 65,536. And so the maximum length that we can then have is 65,535, which would be all ones for all of the 16 bits that we have in the total length field. The identification, the DF, don't fragment, the MF, more fragments, and the fragment offset all deal with whether the packet needed to be fragmented because of it being too big. So we have a maximum limit on the size of the payload that can go into a layer 2 frame. If we're using Ethernet, we saw that the maximum size of the payload of an Ethernet frame was 1500 bytes. If the number of bytes that we have in our entire IP packet is more than that, then we're going to need to fragment our packet. So the identification field is where we would make sure that all of the packets that were fragmented need to have the same identification, so that they all are going to have the be able to be put back together into the same packet when they get reassembled on the other side of the network. If a packet comes in with the DF field set to 1, the DF bit set to 1, that means don't fragment this packet. If you need to fragment the packet and the DF is set to 1, you're going to drop the packet, because that packet would not be able to be forwarded along in the frame if it exceeds the maximum payload of the frame. The MF field is more fragments. This is used to know when the last fragment of a packet has arrived. So the more fragment field would be set to 1 as long as this is not the last fragment in our entire fragmented packet. If it is the last fragment, then that would be set to 0, and this is the indication to the receiver that there are no more fragments coming, so you can piece all of the fragments back together. The fragment offset is how we know the order in which to piece them back together. If the fragment offset is going to be incremented for each fragment that is transmitted. If we only have 5 fragments that are transmitted, we would have the identification on all 5 of those would be exactly the same. We would have the don't fragment field set to 0 because we are fragmenting. We would have the more fragment set to 1 on all of the fragments except fragment number 5. And the fragment offset would be 1 for the first one, 2 for the second, 3 for the third, 4 for the fourth, and then 5 for the fifth. At that point, since we know that there are no more fragments, since the more fragment bit was set to 0, we can then piece all 5 of those fragments back together, and we know that they all go together because they all had the same identification. Okay, down to the third row, the time to live. This is a counter used to limit the packet lifetimes based on the number of hops. So we want to make sure that packets don't just continue circling in the internet or inside of a network if we can't find the destination. So we have a time to live set on each packet. You see that the maximum time to live is going to be 8 bits. So the maximum would be 2 to the 8, which is 256. So the maximum number of hops that we can have is 255 if we set all of those bits to 1. Each time that we go from one router to another, that's considered a hop. The router that receives the packet is going to decrement the time to live by 1. If a router receives a packet and it decremented the time to live to 0, it's going to drop the packet. And so it will not continue circulating through the network if we can't find an appropriate route to the desired destination. The protocol field is used in the data, or this is used to determine what the protocol is that's being used in the data portion of the IP packet. This is not saying what the protocol being used at the segment layer, or at the in the segment is at the transport layer. This is saying what is the protocol used in the data portion of the IP packet, such as, are we using IP version 4? Is it being tunneled? Is it being encapsulated? We often do this when we have an IP version 6 network and we're routing IP version 4 packets through them. So we would tunnel our IP version 4 packet through an IP version 6 packet. Are we using a mobile ad hoc network or an exterior gateway protocol? You can look up all the different protocols. There's over 100 different values that can go into the protocol field. The header checksum is only used to verify the header, and it must be recomputed at each hop since the time to live is going to change. So there is some checking that goes on to make sure that the header of an IP packet is delivered correctly. It does not do any checking on the data, but only making sure that the header was received correctly. We then have to recalculate the checksum before we send it back out, because we are going to decrement the time to live. When we decrement some value or change some value in the header, then it's going to change the checksum as well, or potentially could change it. And then when it gets received at the next router, it would be able to check the checksum against the values of all of the header fields and make sure that we've received the header of the IP packet correctly. We are going to be checking the data in layer 2. So we talked about the data link layer, and we talked about Hamming code and some other checksum strategies and algorithms for making sure that the data received in layer 2 is correct. We also are going to see that we do some checking at layer 4, which is our first end-to-end layer. The options at the bottom, again, were used to allow extensibility of the IP version 4 header. They're not really used by all routers, and since they're not used by all routers, the only time that this would be relevant is if you're within your own network and you have multiple routers that are all going to utilize those options. Since this is not typically the case and not all routers implement them, oftentimes we would have 0 options at the bottom. And then after the options is where we get into the payload of the IP packet, and the payload of the IP packet is the segment from layer 4. Here is a diagram showing you the different classes that we have of IP addresses. IP addresses are 32 bits long. Oh, let me go back to this slide for a second. I skipped over the source address and the destination address. So you see those are going to be the IP addresses right here, the source address, and here the destination address. These are the IP addresses of the sender and the desired receiver of the packet. Those two addresses typically stay the same throughout the entire communication. Even as we go hop by hop through the routers, the IP address of the source and the destination must remain the same. This is how the destination is able to respond back to the source if it needs to send something back. Let's take the example of requesting a web page. So you request a web page from your computer, you substitute in your source address, which has to be a public IP address, into the source address field of the IP header. The destination address is going to be the IP address of the web server that to which you are communicating. As the packet gets routed through the network, When it gets to the destination, to the web server on the other end, the web server is going to try to process this packet, give you what you've requested, and then send you the response back, which is the web page. If it doesn't have the correct source address, it's going to send the response back to a different IP address, which is not what you probably intended. So that has to stay the same throughout all of the communication. The only exception to this is if you are using network address translation at your router. Then your private IP address is going to be used when you're communicating directly with your router. Your router is then going to substitute its public IP address in for the source address, because a public IP address has to be provided for the destination to send the response back to you. When the response comes back, it's going to come back to your router, which was the IP address substituted in for the source. Your router is going to maintain a table mapping the response that comes back from that flow of data back to your private IP address, so that it will substitute back in your address when it comes back and route it back to you inside of your network. Okay, back to our next slide on IP addresses. We see that IP addresses, these are IP version 4 addresses, are 32 bits long. There are different classes of IP addresses, class A, B, C, D, and E, and they're distinguished based on the starting bits inside of the network address. You see that each IP address is broken down into a combination of network bits and host bits. If you have a class A address, you will have 8 bits designated for the network. You see on the right side of this diagram that means that our range is going to go from 1.0.0.0 up to 127.255.255.255. If you have an IP address within that range, you have a class A IP address. You can figure out your network address because that is going to be the first 8 bits that you have in your IP address. The first 8 bits of the IP address is the first octet, which is the first number that we have right here before the dot. We have 4 octets for each IP version 4 address. So with a class A address, the network address is going to be the first octet. For a class B address, we have the first 16 bits of the IP address is going to be designated for the network address. So in this case, we have our range goes from 128.0.0.0 to 191.255.255.255. The network address is going to go from 128.0 up to 191.255 because it's the first 2 octets of the IP address that represent the network address. When we move up to a class C address, we see that we have the first 3 octets, which is the first 24 bits of the IP address that represent the network address. So 192.0.0.0 to 223.255.255.255 is the IP address range. The network address range is 192.0.0 up to 223.255.255, and that would represent the network address. The number of hosts that we're able to have on each network is dependent by the number of bits that we have representing the network address. If we have a class A network, that means that we only have the first 8 bits dedicated to the network address, which leaves us the last 24 bits allowed for the host. That would be 2 to the 24 hosts that we have available to us on the network. Doing a little rough math, that would be 2 to the 4 times 2 to the 20. 2 to the 4 is 16. 2 to the 20 is approximately 1 million. So that's going to give us about 16 million host addresses that can be on a Class A network. These are very large networks. There would be no reason for an ISP to assign a Class A network to an individual person. A Class B address, we have 16 bits for the network and 16 bits for the host. That means that we have 2 to the 16 different number of hosts that we can have on that network. Well, again, doing some rough math here, 2 to the 6 is 64, and 2 to the 10 is approximately 1,000. So that gives us about 64,000 hosts that can be on a Class B network. Again, there's no reason for an ISP to assign 64,000 hosts to an individual's network. There are probably very few companies that even need that many public IP addresses on their network. At UAA, we do have a Class B address, all of the IP addresses. If you're on campus and you're wired into one of the network ports at UAA, they all start with 137.229, and then they have the host bits after that. So we do have a Class B network assigned to us at UAA. It's actually assigned to the entire UA system. A Class C network has 24 bits dedicated to the network, and we have 8 bits dedicated to the host. That means that we're going to have 2 to the 8 potential hosts on this network, and that's going to be 256 different hosts. This is getting down to a little bit more reasonable of a point for individual users. However, 256 public IP addresses is still probably way too many for a personal network. Because of that, we have another technology that we're going to talk about, which is subnetting, and we'll get to that in a little bit here during this lecture. The Class D and the Class E addresses are used for other purposes. Class D addresses are used for multicast. This would be where a single computer may want to send a message to a set of other computers, and you would have a multicast address set up, and the routers would then be intelligent enough to know that when a message gets sent or when a packet gets sent to that multicast address, it is automatically going to forward it to all of the other IP addresses that are part of that multicast address. And the Class E address was reserved for future use, research use. These are just unassigned IP addresses that can be used for whatever purpose that you'd like. They are not considered public IP addresses for being able to communicate on the internet, but you can use them in your own applications knowing that they're probably not going to conflict with other IP addresses that are being transmitted. Okay. There are a few special IP addresses that we have. If you have an IP address which is all zero, so 0.0.0.0.0, that is always going to refer to the current host. If you have just the network portion of the IP address as zeros, and then you have numbers for the host address, that is always going to refer to a host that's on the current network. If you have all ones specified, that's going to be broadcast on the local network. That means that you're going to send this packet to all of the computers that are on the network. If you have a network address specified in the network portion of the IP address and all ones specified for the host address, this is going to be a broadcast sent to all of the computers on a distant network. This is usually something which is blocked by routers coming into a network. They don't want computers to be able to broadcast messages to all of the computers that are within their local network. So this is typically going to be blocked by most routers. And then we also have the loopback control. Most of you may know that if you specify 127.0.0.1, that is the loopback. This is going to bring the packet just straight back to your computer. It actually can be 127.anything, but 127.0.0.1 is traditionally how we loop back to our current computer. So a little more information here about IP addresses. It has to be a unique address required of all computers that communicate on a network. So if we are within a network, our IP address has to be unique. It's the unique way that we can identify our computer on the network. Think of this like a physical address of a house, and you can't have the same address on more than one house. If you want to send a letter to somebody, you have to include not only the number, the street, but you also need the city, the state, and the zip code. Potentially the country, and other countries have different addressing schemes as well. So an IP address has to be unique. If we're communicating on the internet, it has to be a unique public IP address. So nobody else in the rest of the world is going to be able to have that specific public IP address. If they do, routers are going to get confused along the way, and they're not going to know to which destination to send that packet. So you have to have a unique IP address if you're going to be able to communicate on a network and then receive responses back. We have IP version 4 addresses that we've discussed that are 32 bits separated as 4 numbers of 8 bits each. There's an example. This is a UAA IP address. I know this because it starts with, it's a class B IP address starting with the network address 137.229. The host address is 154.221. And for those of you who are curious, I just pulled this number out. This is not the IP address of my own computer. With IP version 4, we had 32 bits for each host. That meant that we had potentially 2 to the 32 different computers that we have available to us in the world. Well, 2 to the 32, doing a little bit of rough math here, is 2 to the 2 times 2 to the 30. 2 to the 2 is 4, and 2 to the 30 is approximately 1 billion. That gives us 4 billion IP addresses. Public IP addresses. Well, as we have multiple public IP addresses associated with individuals, either an individual person has more than one public IP address, or we have companies or corporations that have hundreds or thousands or even tens of thousands, hundreds of thousands of public IP addresses associated with them. We have gotten to the point where we have run out of public IP addresses. The solution to this was a little band-aid we had was using NAT, which is Network Address Translation. So we can have just the public IP address on the public-facing router to the internet, and then we can put private IP addresses within the network. Well, you can have a computer with a private IP address in one network and another computer with a private IP address in another network. That's exactly the same because they're in different networks. When we're dealing with public IP addresses, they're all on the same network, which is the internet. So they all had to have unique public IP addresses. So the solution then, since natting has a little bit of overhead also because we have the routers that then have to perform that translation and keep track of tables, mapping them, and so on. So IP version 6 came out to try to fix the problem. It was standardized. It's already being implemented in newer operating systems, and you see that it has 128 bits for each of the IP version 6 addresses. That means that we have up to 2 to the 128 different hosts available on the internet, and that is a number so incredibly large that it is probably going to take quite a number of years, if not decades, is my prediction, before we run out of IP version 6 addresses. IP version 6 addresses are separated as 6 sets of 4 hexadecimal values. Hexadecimal means that we have the values 0 through 9 and then A through F. A being 10, B being 11, and then all the way up to F being 15. Here is an a sample IP version 6 address. So you see that we have 4 hexadecimal values, then we separate it with a colon, 4 more hexadecimal values separated by a colon, 4 more, and so on all the way. So we have 1, 2, 3, 4, 5, and 6 sets of 4 hexadecimal values. Each hexadecimal value can be from 0 through 15. That takes 4 bits to represent each one of those. That means that we have 4, 8, 12, 16 bits to represent each one of these sets. 16 times 6 okay, so let me correct what I just said. IP version 6 addresses consist of 128 bits separated as 8 sets of 4 hexadecimal values, not 6 sets of 4 hexadecimal values. And so you see here in this case that there are 1, 2, 3, 4, 5, 6, 7, 8 sets of 4 hexadecimal values. Each one of these hexadecimal values has 4 bits, so that's going to be 16 bits that we have for each one of these sets of 4. 16 times 8 is then going to give us our 128 bits. A note on hexadecimal, IP version 6 addresses: if all 4 of the hexadecimal values are 0, they get omitted from the address. So take a look at this one right here. So you see that I have these first 3 sets of 4 hexadecimal values all like that, and now we have 2 colons right next to each other, and that is going to be omitting the 4 zeros that are in the middle. Now here's the tricky one, is that if there are trailing zeros at the end, they just omit the colon and the other ones after that also. So this is actually omitting the 7th term, which is 0, 0, 0, 0, followed by a colon, and then the 8th term, which is also 0, 0, 0, 0. Okay, public IP addresses are those that are able to be seen by any computer in the world. Private IP addresses are typically secured behind a firewall. We have to use network address translation to get private IP addresses because they're not able to communicate on the internet. They're only able to communicate within their local network. If they're going to communicate on the internet, then they're going to have a public IP address to use to transmit out, and this usually comes from the router, which has the network address translation built into it. Private IP version 4 addresses are in the following ranges. If it's a Class A private address, it's going to be in the range from 10.0.0.0 up to 10.255.255.255. A Class B private IP address is in the range 172.16.0.0 to 172.31.255.255. And then the one with which most of you are probably most familiar is the Class C private IP address, which is going to be in the range from 192.168.0.0 to 192.168.255.255. This is typically how most routers come configured, is with a Class C private address range for any of the computers that are connected to it. You also may have seen once you have your computer and you're trying to communicate on the internet or on the network, and if you're unable to obtain an IP address, you will get an IP address typically in the range of 169.254.0.0 to 169.254.255.255. These are not available to the internet. These are IP addresses that are invalid, and this is just your computer's way of telling you, hey, I was unable to acquire an IP address, so I'm going to give you the error IP address, which is one in the range of 169.254. To find your own IP address, you can go to, in Windows, go to the Start menu, and then in the box, type in CMD. That's going to open up a command line window like you see right there on the screen. And then type ipconfig in the command line window. You're going to have a lot of things that pop up, but something that you'll see here, I have a few different adapters on my computer that I use to take this screenshot. So you see that I don't have any Bluetooth connected, I don't have anything to my second local area network or to my mobile broadband connection. If I happen to have a SIM card in my computer, then I would have had that also. I have 2 connectors though that are hooked up to adapters, which is my wireless local area network, and you see that I have my IP version 6 address here. Here's my IP version 4 address, so it supports both IP version 6 and IP version 4. We're going to have to support both of those versions of IP for quite some time. We're not going to be able to say, as of January 1st, IP version 4 is no longer used and only IP version 6 is going to be. We can't do that because IP version 4 devices exist that don't use IP version 6, and it's a tremendous investment for a lot of companies and organizations to upgrade all of their hardware to using IP version 6. This is going to be a gradual transition, and until we have enough devices where we are able to just flip the switch, we're going to end up having to support both IP version 4 and IP version 6 simultaneously. The subnet mask we're going to talk about in just a second, and the default gateway. This is going to be the router or the computer that all of your traffic will go through before it makes it out onto the internet. At home, your default gateway is going to be configured to be your router. At work or in companies, this may be configured to be a computer through which all traffic flows so that the company is able to monitor traffic coming into and out of the network. We see the same addresses on the Ethernet adapter, the local area connection. Now, something that you notice here is that the wired connection, which is my Ethernet connection, I have a 137.229 network address. That means that I have a public IP address on my computer right now if I'm plugged into the wall. However, on my wireless LAN, you see that my IP address is a 172.16. Well, we saw that that was a Class B private IP address. So when we're on the wireless network at UAA, we are going to have a private IP address. When we're on a wired connection at UAA, we have a public IP address. DHCP stands for the Dynamic Host Control Protocol, and it's used for a computer or router to automatically assign IP addresses to computers on the network. These IP addresses do not have to be private IP addresses. Oftentimes they are, but they don't have to be. In fact, what we just saw on the previous slide is that my wired internet connection received a public IP address from the DHCP server. So the addresses assigned to each computer can be either private or public, but this is just a way so that we don't have to statically configure all of the IP addresses on all of the computers within the network. That's a little bit more overhead, a little more work for network administrators to take care of, so it's a lot easier to let the router or the which usually implements the DHCP server, take care of assigning IP addresses to all of the devices that are on the network. Most DHCP servers will assign private IP addresses. Your routers at home that have DHCP enabled on them most likely are going to be assigning 192.168 IP addresses. You see here on campus on the wireless network we're assigning the Class B private IP addresses rather than the Class C private IP addresses. Okay, subnetting. Since network addresses are so scarce, we can take a few bits away from the host address to make a subnet within a network. Remember earlier I said even a Class C IP address or a Class C network still has 2 to the 8 host bits, which is 256. Well, this is way too many hosts for a personal network. I only have one public IP address on my home network because I have from the wall it comes into my modem, and from the modem it goes into my my router. My router has the public IP address on it, and all of my computers that are inside of the network then have private IP addresses. Even if I was going to have private IP addresses on all of the computers and devices that I own, which that wouldn't be necessary for a home network, it would still only be a handful of public addresses. It wouldn't be 256, which is how many we get with a Class C address. So subnetting allows us to take a network address and take the host bits from it. Or sorry, let me say that again. It allows us to have an IP address that has a network address portion of it, but then instead of having the entire number of host bits dedicated to hosts, we can take some of the host bits away and dedicate that to what's known as a subnet, which is a subnetwork. And then we can give out subnetwork addresses to multiple people as opposed to having to give out an entire network address. This works extremely well for ISPs who are only going to be assigning 1 or 2 IP addresses to an individual person. That means that possibly all of the computers or all of the subscribers within a neighborhood are going to have the same network address, but then the ISP is going to assign each individual subscriber with their own subnetwork. So let's take a look here at this example that I have. Assume that a host has an IP address 74.125.127.104, and we have a subnet mask 255.255.255.192. We're going to write out both of these numbers. So here's the IP address down at the bottom, 74.125.127.104, and then the subnet mask, which is 111.111.111.110.00000. All subnet masks have to have ones from the left side forward, and the first time that you get to a 0, you have zeros the rest of the way. The reason for this is that we see that this 74.125.127.104 is part of what class of IP addresses? Okay, hopefully you all got this one correct, that this falls into the range of a Class A IP address. So that means that we actually have just the 74 as the network address. So only the 74 is the network address since this is a Class A address. And the rest of these 24 bits are going to correspond to the host address of this IP address. So what we've done now is we've said, okay, instead of just the first 8 bits being network address bits, we're going to take the first 8 as network address, and then we're going to take the next 8, 16, 17, 18. The next 18 bits are going to represent our subnet. Then we've reduced this down to only having the last 6 bits as host bits within this subnet. So we can figure out the subnet address is going to be figured out by just ANDing all of these values together. So when we AND these values together, we are going to get the value. When we have a number ANDed with a 1, we just get that number. When we have a number ANDed with 0, we get 0. So our subnet is going to be the first octet, which is 74. The second octet, which is 125, the third octet, which is 127, and then followed here we're going to have 0, 1, followed by all zeros. Well, to figure out what that is, I'm going to cheat here a little bit. And let's just grab our handy-dandy calculator here. And we have a 0, 1, followed by 6 zeros. And we want to convert this to decimal. And you see that it's 64. So our subnet address is going to be 74.125.127.64. How many hosts can we have in the subnet? Well, we have 6 bits remaining for host bits within our subnet. That's going to allow us to have 2 to the 6, which is 64 different hosts within our subnet. Okay, here is another example of getting the to get the network address from an IP address and the subnet mask, perform a logical AND operation. So what we have here is we have an IP address and we have a subnet mask. We have a subnet mask for all of our IP addresses if we're going to be using subnetting. So you see here is an IP address on the top. And I've already separated them out into the bits so that we don't have to do the math this time. Here's our subnet mask. You see that we have all 1s until we get to our first 0, and then we need to have all 0s following that. And then we just start ANDing these bits together, and this is then going to give me, in this case, this is going to give me my network address. So here I have um, all of my, so here's my 137, here's my 229, and now here's where I start to get a little different because my zeros start. So I'm going to do the 1 and 1 gives me a 1, the 0 and the 1 gives me a 0, the 0 and the 1 gives me a 0. From that point on, it's all zeros because 0 and anything gives me a 0. So here these are going to be all zeros the rest of the way. Figuring this out, we see that I have 137.229.128.0, and that is going to be my subnet address. Looking at this again, hopefully you can answer the question, what is the what class IP address are we looking at here? Okay, hopefully you got that right. 137.229 falls into a class B IP address. So the network address is 137.229. The subnet address is 137.229.128. And then with this subnet, we then have 1, 2, 3, 4, 5 plus 8, which is 13 bits left for the host address. So that would be 2 to the 13 potential hosts on this network, which is going to be approximately 8,000. It's going to be 8,192 is the exact number that we have. So that gives you a little introduction here to subnetting. I'm going to go back here to this slide just for one more second because we have a different way of writing this out, and this is typically how you're going to see it written. When you do your homework problems from the textbook, you're going to see IP addresses written out in this manner. So looking here in the middle, you see that this is just the IP address written, but then there's a slash. This is called the slash notation. We have a /26. What the 26 tells us is the number of network bits in the IP address. Now, this probably should say the number of sub-network bits that we have in the IP address rather than the number of network bits that we have. There we go. Because we know that this is a Class A IP address. So we already know that there's only 8 network address bits in this IP address. However, since we have a subnet mask, which in this case is 255.255.255.192, that's going to tell us that we have a subnet which consists of the first 26 bits of this value. The way that we get this number 26 here, hopefully you can see the significance of that 26. This is going to be the number of ones that we have in our subnet mask. So we have 8, 16, 24, 25, 26. And that's where you get this /26. This is just the preferred method for writing out an IP address with the subnet mask, because otherwise you would write out the IP address like this, and then you would write the subnet mask out like this of 255.255.255.192. And then have to figure out that 192 is 11 followed by 6 zeros. Instead, if you write the IP address out with the subnet mask like this with the /26, it's a lot clearer that you know, okay, the first 26 bits of this IP address are going to represent the network and the subnet. We can figure out the network address because we know this is a Class A address. We would be able to figure out if it was a Class B or a Class C address also, just based on the values in the IP address. And then we can figure out how many bits are being taken away from the host so that we can determine the number of bits used for the subnet. So in this case, we had originally, since this was a Class A address, we had 8 bits for the network, and we had 24 bits for the host. Since we were going to use 26 bits for the subnet, 8 of those bits were already the network, so 26 minus 8 is going to give me 18 bits that we're taking away from the host, which leaves us with 6 bits for the host, and those 18 were taken away from it to be added to the 8 bits from the host and make the total of 26 bits for the network and subnet address. Okay, our last slide in this lecture is on network address translation, which we've already referred to a few times in this lecture. It's sometimes referred to as IP masquerading because this is exactly what it's doing, is that we are masquerading our IP address and changing it from this private IP address to a public IP address, and our router is masquerading as if it is us. Private IP addresses are only able to be accessed by hosts inside of the local network. They are not able to be accessed by hosts that are outside of the local network. If a host outside of the local network wants to be able to access a computer that's inside of the network, they have to specify the public IP address of the router. The router then will allow or disallow that traffic from coming into the network. The router, or whichever computer you have, which is determining that's performing the network address translation, has to maintain a NAT table, and that links the private IP address and the source port, which could be TCP or UDP, to the destination IP address that we've communicated with. So when the destination writes us or sends us the message back, it's going to send the message back to us with the public IP address in the packet, but it's going to have as its destination port the source port that we specified. And this port is what's used for network address translation. Since we've already talked about ports are not in layer 3, they're not in packets, but instead ports are in segments. They're in layer 4 segments. So what that means is that to perform network address translation, we have to grab one little thing out of the layer 4 segment, which is just the source port, so that we can perform appropriate network address translation, and the traffic is able to be routed back into the local network to the correct host. Hopefully, this has taught you a lot about the configurations that you have set on your own routers. I encourage you to log into your routers at home and take a look at the settings that you have for DHCP, the settings that you have for NAT, and you can also look at the public IP address that you're assigned and the subnetting that your router has assigned to it from your ISP. And chances are you're probably going to have something like a /29, a /30 perhaps for your subnet, because you only have a couple bits, so you can only have 1 or 2 public IPs on your network. Most companies are going to have at least 2 public IP addresses on the network, because your modem is going to get one of them, and then your router is going to get another one. So you probably are going to have 2 public IP addresses on your network is what you will need. All right, I hope you all enjoyed this lecture. Homework 3 is posted. You can be working on that. Start looking at the homework number 4 also, which is on chapter 4 of Tannenbaum's book. And if you have any questions, of course, feel free to send me an email or get in touch with me.